All right, welcome team. Session 3 of our session of our program, AgenticAI. So we are today going to discuss about the embeddings, embedding models, and how it is related to the GenAI or AgenticAI or the chatbots applications, and how it is part of this RAG architecture. Tomorrow we'll get into the vector databases, and then we see how we combine embedding models, embeddings, and vector database to build a semantic search application. Okay. Now, this is something that we have learned last week, the RAG architecture, right? I hope you remember this. Let me get into this now. So the RAG architecture. So anybody can anybody recall what problem RAG architecture is solving for us? Okay.
Internal company related data we can extract.
Correct. So since the LLMs does not have access to the confidential or personal information or the organization information, what we do is we build a RAG architecture, and then we provide our information through RAG as a context to the LLM model. Okay. So last week I was talking about the top part here, documents, chunks, embedding model, all of this, vector database. So this all comes as a retrieval process. Okay. Then combining the context, whatever we get the search results from vector database and the query into a prompt template is called augmenting your prompt. You're not just sending the query, but you're also now sending some of the results from this to your LLM model. So that is called augmented. Now you send this question and context to the LLM model, and then it generates a response. So that is generation. So that's called RAG architecture, retrieval augmented generation, right? Now, doing in all of this, the first part is setting up the library or knowledge hub information where you go and search, get the. It's basically very similar to what the information you have in your organization. It can be your HR database, or it can be your orders, it can be your financial AP, GL, invoice, whatever orders, support, tickets, whatever information that you are currently storing in your databases, right? It might be Oracle, SQL Server, MySQL, Databricks, Snowflake, whatever it is. All that information can be your knowledge, okay? Or just your documentation, like PDF documents or text documents, CSV files, all of that can also be your knowledge hub, okay? Let's say all your, I keep coming back to the same example every time so that we can all relate to it. Let's say if we go back to our HR policies, right? HR policy information that we do. That's our knowledge hub. We want to give the complete policy, HR policies to our application, internal chatbot. So let's say we are building internal chatbot for the employees where they can ask questions about the HR policies and then get the answer immediately instead of them going back to the benefits, logging into all of their ESS and employee self-service, going through a lot of documents, right? All of that. You just go and ask the question in the chatbot. It will give you the response. Again, all of that access related thing happens, but it will give you the response immediately, right? So to build that, so that chatbot, the first part is to build a library, okay, knowledge base or whatever you call. So not just internal, it can also be used in the agentic applications as well, okay? When we talk about agents and agentic application, we will get to know that there will be some tools, and those tools will have resources to get information from. and your complete RAG can be one of the tool or one of the resource for the agent to get the information from. Okay, that's where it plugs in. We'll get back to that. But remember, so this is what we will be doing this week and next week, the complete RAG architecture. Okay. Today we'll talk about this part, embedding models. So what is an embedding model? What is an embedding? Why do we need embeddings? How we use the embeddings in the context of the RAG architecture. Okay. And then when we talk about vector database, we will also add these two components here. So we will do the first retrieval part, complete by tomorrow. Then we will do this next week, RAG and building RAG applications and all of that. Okay. Now let's get back to the retrieval embedding models, what we are doing with the embedding models. So we'll go here. I have to copy that slide, so that was missing. Didn't save last night. So embeddings and embedding models. Now, last week, I think we slightly touched upon embeddings. So what does an embedding mean? What does an embedding mean? Guys?
It is a powerful deep learning technique to convert each chunks into dense vector and that capture its meaning.
Vector encoding of text. Okay.
Yes.
Okay.
Yes.
No, it's not a deep learning technique. It can be used in that, but what embeddings is just a numerical representation of your text or image or audio or video, whatever it is. Convert all of these modes or all of these formats into a numerical representation. Since models understand the numbers very well to compare, contrast, search, all of that. So it will compare the text with to the numbers. Now you can say, why do we need an embedding model and embeddings to convert that? We can, in general, convert any text to number with, say, hashes and all of that, right? You can generate in using the libraries. You can generate hash keys or whatever from the text. You can convert that kind of thing. Embeddings, what they do, they don't just convert the text into numbers. They also safeguard the context. They also make sure the context of the text is preserved in that embedding model, in the embeddings that they generate. So that's where it helps when you do a semantic search, like similarity search, not the exact search. So what you do in SQL, you write numbers or text in a table, and then you do a SQL class. But in embeddings, when you convert it and store in the vector database, you do a similarity search. You don't do exact search. Of course, there are like after the RAG, there is a new technique or framework called hybrid RAG, again, where they combine both the traditional standard SQL based search to filter and then apply vector database, vector search as well, semantic search as well. But that's a hybrid RAG. For now, we'll stick to this. So to do the semantic search, similarity search. So these are useful. Okay. Now, what does an embedding look like? So we talked a little bit about this. I'm not sure if we have looked into this, but an embedding is just a vector list of floating numbers. Okay, so whatever you do, you provide your text. Let's say I'm in general, I'm talking about text. The same applies to image or audio or video embeddings as well. So I'm taking the reference of text for now. So let's say you have a word or you have a sentence, and then you pass it. It's like a machine, right? Or a black box. You pass that into the model, an embedding model, which is trained to generate a set of numbers, okay, floating values, which is called a vector, dense vector. How many variables or how many elements are there in that vector depends on what model you are choosing. Again, just like your large language models, embedding models also come with a predefined set of variables that they can generate. It's called dimensions. Okay, so each model will have a dimension. So whatever word or sentence or paragraph or a document you put in, it will output a set of numbers with a fixed dimension, predefined dimension. When I say fixed dimension, some models also give you flexibility to choose which, what is the dimension that you want to use. So we'll come to that. What is dimension and how do we use those dimensions and all of that. Another parameter that embedding models do is the size, how much you can input into the model at one time to generate an embedding. So these are the two parameters. One is the size of the size of tokens, the number of tokens that it can take at a time to generate an embedding out of it, and the dimensions that it gives you. These are the two parameters that the model, and then there is always multi-model. Some models can also do both text and images as well, but there are models specialized specifically for those. Like some are only for text, some are for image, some are for audio, some are for video, those kind of embeddings that they can generate. Okay. Now, as I said, embedding is a vector list of floating point numbers. If you see here, let's say I have a word called man, and its representation in embeddings is this. Okay, some set of numbers. You can't make any sense out of it, with human eye, what it means, but the machines can. If you put woman, again, you will get all of these numbers, floating point numbers. So this will represent a woman, and king and queen. Okay, so all of this. Now, when you do a similarity search using these embeddings in the vector database, so the distance between these two vectors measure their relatedness. So this is a floating, this entire thing is, let's say you think of it, you have done graphs, right? X coordinate, Y coordinate, you take X, Y coordinates, and then you plot that point in the graph somewhere. You have another point, you plot that, and the distance between those 2 points you can measure using the formula, mathematical formula. Now the same thing also happens here to see how two given two vectors, how are they related, depends on how close or how far they are in the n-dimensional space. Now when we talk about graph paper, we can only visualize a two-dimensional, right? X and Y coordinates only. Now then there is a three-dimensional. Now similarly, this becomes n-dimensional. N-dimensional means the same point is plotted across all of these dimensions. How many dimensions? As I said, it is defined by the model that you are using. So these can be a set of 536 numbers, that will represent just one word called man. And it can be 1500 set of 1500 numbers, or it can be 5000. Depends on how complex or how big is your embedding model that you're trying to use. And again, as I said, the dimensions are fixed. No matter you input one word or you input 1000 words, tokens, you will always get the same set. The number of elements in that vector will be same based on the vector model. So if I take an embedding model which says dimension is 500, if you put one word, it will give you a vector of 500 elements. If you put a paragraph, it will still give you the vector of 500 elements. If you put an entire page document, it will still give you the same. So the output is the vector dimension is fixed. Okay. Now visualize this in an n-dimensional space. When you plot, the distance between these two will tell you how these are related. Okay. This data could consist of words, in which you call word embedding. It can also represent image, audio, and even large chunks of structured data as well. Okay, so what we are trying, we did when we created the search algorithm or deduplication algorithm for an MDM application using the structured data. So what we did was we converted the structured data into a meaningful sentence or a paragraph, combining all of those attributes of a person, and then fed that to dimensional model to get the dimensions and vector databases to do the similarity search. Yes, Lakshman, you had a question? Have a question?
Yes, Harun. So we whatever the model, uh, it will have some fixed number of size. Size is we got it like for every word we get the same number of tokens. But are the tokens are same always for the same word? Always in the sense at your environment or maybe my environment, if we are using the same model, my vector tokens and your vector tokens are they same or different?
It should be similar. It may not be same. Okay. Again, it is also a model which is trained. Okay. It's also a deep learning model that is trained to generate the numbers. Now, why I say that is when we do this semantic search, when we say what are the limitations of this semantic search model, one of the limitation is the dimensions and the embedding model you are choosing. Now, as you said, what happens, environment is fine. Even if you change environment, as long as it's the same model, it should give you the same embedding for the same input. But if you change the model, okay, even though you have, say, you have two embedding models with the same dimensions, but both of them will give you a different output, okay, for the same word. So that's why when you choose a model, you got tied to that model, you know. And the other thing is dimensions. Once you choose a dimension, you cannot change your dimension. Once you change that, it will not accept if you change a dimension. So you have to, even if you change embedding model or if you change dimensions, you have to rerun all your input data to generate new embeddings. So those are the two limitations that it has. But to answer your question, yes, once you change the embedding model or change the dimensions, your numbers will change. But if it is the same model, you should get same output. We can check that, but we will not be sure because the kind of the vector that you get is a very huge decimal number with 500 elements. It's not a straight comparison of first element, second element. It's combination of all those 500 or 1000 or 1500 elements in the vector. Okay.
Okay. Thank you.
All right. So now using these 500 numbers, so it's that point lives in an n-dimensional space, 500 dimensions. It's plotted into a space, embeddings. Let's say when you store in a vector database, it's stored here, and the distances between those two is calculated by the retriever or the vector database when you search for it, two dimensions, and then it will give you the relevance, how close they are or how far apart they are, in terms of it. So you can compare these four: man, woman, king, queen, and then you get some relevance. First, you get which matches closely, and then it will also give you a score, how close they are based on the distance. So there is a distance between the points you get, and then it can also be the a score that you get to see how close they are related. Okay, you get that? So where do we use embeddings? Why does embeddings matter in the GenAI? Fine, you said beautiful. We'll take model with 1500 dimension or 5000, put all the data into it, get embeddings and store it, and then search get. But why do it? why not use the relational database? Where it is applied, right? So results in the search queries, results ranked by relevance to query strings. When you search for a semantic search query, so let's say, hey, give me all the or what you called products which are used or which are used for skincare. Okay, so there might be a relational database which is tagged as skincare, or if you just have the descriptions in a tag, it can get semantic search out of it and say which ones are used for skincare products, and then they can dump all of that. Semantic search, that's like searching for a meaning with the meaning, not just the straight word in that. Clustering is when you want to group text strings by semantic similarity. So let's say you're doing, it's more close to classification also, where you're saying, right, you want to classify positive, negative, and neutral sentiment. You want to classify, or you want to cluster based on the characteristics. So even if the text does not have the actual word, it can identify the meanings. If you say good is same meaning as let's say awesome or happy or something like that. Negative words, it can understand what are the negative words which can lead to negative sentiment and classify that accordingly. So those are the meanings that you get where you cannot do an actual search. So if you have all the comments, right, how do you search for a positive or negative? You have to build a huge algorithm to search for the kind of words in that complete text and then write to that. But if any of the word changes, you have to always go back and change all of that logic, right? Now, using the semantic search, the models can understand what it means. You don't have to put in keywords and then say, you can give some examples. Hey, if this comment is like, I like this product, it is a positive sentiment. Okay, so something like that, you can give examples. But when you search for embedding models, which customers are in positive given sentiment, it can be anonymous, how many or what kind of, so you can do this similarity search. Recommendations is one most popular use case that you apply. If you have related content, if you have watched some show, of course it works with metadata and tags, but still it can identify similar shows based on your history, what you have watched. You like sci-fi, or you some different genres or emotions, or what you have liked earlier, you input that you have given. Based on that, it can search, it can do a similarity search and then get related content that is related to what you have watched. All your algorithms on even the what you call your social media content keeps generating based on your viewing history, right? So all of that is a semantic search that is happening based on your history, that what you have watched. Anomaly detection, you can do outliers based on the clustering. If some point is coming in falling very huge apart from the normal distribution, you can flag that as a fraud or whatever based on the characteristics. So you can do diversity classification, label matching, and all of that in the using the semantic search. So basically, wherever you need a similarity search, chatbots, you need the RAG architecture or the embeddings. It's faster to retrieve, plus it has the meaning that is preserved, the context that is preserved. Okay, once we get into this, so this was again, I borrowed the slide from tomorrow's session, the vector search. Once you have generated the embeddings like this for any of the words or sentences, I said we'll plot in n-dimensional space. So again, we are only showing 3 dimensions here because we cannot visualize that. But let's just think about visualizing it in n-dimensional space. The embeddings that you generate, for example, for a cat, dog, wolf, will fall in the space. The dimension, the embeddings that you generate for fruits, say apple or banana, will fall here. Semantically, or if you say clustering, these are very pretty far apart because these fall in fruits, these fall in the pets and animals and etc. and all of that. Now, when you search for a kitten in the semantic search, if you do a SQL search, you will not find that word at all. Okay, even if you say like kitten, you will not get anything in the relational database. It will not return any results. However, if you search in the vector database, it will give you the n nearest neighbors, the closest neighbors, by calculating the kitten is converted first into the embeddings. And that embedding is, it will say, hey, where it will fall in this space. So let's say kitten falls here based on the embeddings that it has generated. Now, using that embedding, it will search who are my nearest neighbors. So it falls very close to the cat because, cats is the baby is the, I think, kitten. So it will get this. Now, what is next closest? Dog. How is kitten related to dog? It's not, right? But if you look at the holistic picture, cat and kitten are same, but not dog. Okay. But if you look at it, both cat and dog are pets, right? So if you're talking in terms of context, you can ask, hey, what are the pets? Then it will say dog and cat. So because these are both close to each other. So the most closest to kitten is cat. The next neighbor can be dog. Okay. Next can be any other, parrots, birds, whatever may come here. Then there is a wolf. Wolf is not a pet. Okay. It's still farther away. But however, they all fall into the classification of animals. Again, there might be a classification, domestic animals versus wild animals, kind of a thing. So they keep going farther and farther. But still, they are under the same. Now, extremely different on the other side is, fruit, because wolf, dog, cat does not have anything common with banana and apple, unless you say in a sentence, I am feeding an apple to the cat, or I'm feeding a banana to the dog. In that context, if you have, which is not very common that you see when models train and learn, where it occurs in any context, right? So that's how they are like apart, the distance between them in the n-dimensional space that you do the search for. Okay. Any questions here? We will go to our demo in a few minutes. You will get more clarity on what we are trying to do. But in the concept, any questions?
So, Harun, just a quick thing. In the embedding model, you generate this floating numbers, and there is whatever is, lower the distance between it means that they are closer, right? Then is it like that by using the same principle, like, so you have grouped together, let's say, different floating numbers. So all these things like wolf, dog, cat, kitten, they will have a floating number which will be near about, right? Of course, query and cat will be nearer than cat and dog, but it will have a cluster of those kind of floating numbers. And when you are populating in this vector DB, is it automatic population, or how does that happen? Is there a mechanism for that thing, or?
Yeah. So when you store the embeddings into a vector database, that we will talk about tomorrow, there are techniques how a vector database stores this. One is called indexing. It does the indexing. Based on the indexing, there are some algorithms, HS and W and other algorithms that it will use, k and nearest neighbors, all of those techniques. it uses to store this in the vector space. It's called indexing. It will index.
Okay.
Now, when you search, there is again another algorithm that is used to search. I know we have done this in the previous
cosine
classes,
algorithm.
right? The cosine,
Yeah.
cosine distance, the dot matrix product, and the linear distances, right? That we will discuss tomorrow again. So using those algorithms, it will calculate the distance. It's not straight calculating the 2 points in 2 dimensions, right? It's across 500 dimensions or 1000 dimensions, 1500, 5000. So it uses all of those algorithms to get the distance between those two products. Now, to answer the question, yes, when you store it in the vector database, it automatically indexes based on the your embeddings in that space.
Okay.
Okay, that's why the dimensions are tied. When you store the database, you first inform the vector database that, hey, I'm going to store these embeddings with this dimension in the collection. Okay, so then the vector database will know how to store it based on how many dimensions it has and how to index that.
Okay.
I have one question.
Yes, Rajesh.
So this categorization which happens in vector search, like animals in a different category and fruits, maybe other categories, how this happens, or this has to be done by a like AI engineer only?
No, there is no categorization that happens. Okay.
Okay.
That is just I'm trying to explain you why these points are closer than the other ones. Okay.
Okay.
Now, the categorization already has happened within the embedding model that you use based on its training. It has been trained to understand that these are all falling into the same category. Cat, dog, and wolf. Based on that, it will generate the embeddings. We don't do anything, any categorization. We don't tell anything to the model and anything. All we do is just throw the text at it. It will throw the output as a embeddings. That's it. Now, everything else is internal to the model, how it is being trained.
Yeah, okay. Maybe I joined 6-7 minutes late. Maybe you have.
No, that's fine. That's fine. You are good. Yeah, that's a good question. Good question. Yeah. All right. Okay. So let's move forward. Right now, it's just again key features. What is a dense vector? We have seen the set of numbers, right? A dense vector is a fixed length array of numbers. This is what you have to understand. It's always a fixed length. No matter your input is one word, one paragraph, one document, whatever it is, as much as the model can take, it will always output the fixed length array only with the numbers. Okay, if it is 500, 500, 1500, 1500, whatever is fixed, it will always generate that fixed length dimension, because that's how it has to, when you match, right, it has to calculate the distance. So it cannot calculate the distances between two vectors if they have different dimensions. Okay, and where every dimension has a non-zero value that is automatically generated by the model. So it's used to represent input data. It can be text, images, audio, whatever it is. Semantic similarity is preserved in vector space. That's what we are talking about. It's called semantic similarity. If you say here, dog, wolf, cat, kitten, these are semantically similar, not actually same, but semantically similar. They are preserved, the similarity. And apple and banana, because they are, same, fall in the fruits category. Context aware, which means it will take the entire context of this sentence, not just the words and their meanings, but how the word is used in the entire context. Let's say if you're using apple can be used in the context of a product, like we see here, and then it's closest to banana. You can also use apple in the context of a phone, okay, an iPhone. So you can say Apple Pods, Apple AirPods, Apple phone, which is the context is different. Now it should not fall some close to banana here. It should fall somewhere with the electronics, something with Samsung or TVs or all of that. It should fall the Apple when you use the context of Apple in the phone, with the electron, the phone, Apple phone you're referring to, or Apple AirPods you're referring to. The context is different. So that point, the same apple in the sentence, when you use, it is plotted in a different space in the vector database, not with the fruits. So it preserves the context as well. It is a context aware. In what context have you generated the embedding for that particular token or that sentence kind of a thing. And it is compatible with vector search and similarity scoring. Vector search, of course, when you generate the dimensions, you cannot use it as is. It doesn't make any sense unless you do store it in a vector database and do a vector search for that. And then you can also do a similarity scoring. So based on the score, you will know, hey, give top 3 nearest neighbors or top 5 closest ones. How many similar items you want to get out of the vector database as the results. That's how you use it in the use the embeddings in the vector database. Okay. So these are the most important features that you should understand. Of course, we will see the dimensions. So what are different types of embeddings? We have been talking all through this presentation that there can be text, it can be image, it can be audio, it can be multi-modal embeddings, right? So text embeddings are the ones which convert the text into embeddings. Image is like you give it an image, it will convert into a vector representation of that image. Now, another important thing here in the image specifically is, let's say you generate a embedding for a picture of a cat. Okay. Now, how does the models recognize? As I said, it was like in the deep learning also. Image recognition. You kind of say match the images, right? Now you give another cat or a dog of one breed image, and then it generates embeddings. Then you can give another image and say, hey, get me similar images. How does it do? It kind of again converts that embeddings and then search the vector database which has similar embeddings, and then you get it the images corresponding to those, as a okay, this image is what is similar to the one you have provided. So that kind of where for matching the images, it's very powerful and useful. Text, again, you can match using percents equal to some extent, but images you cannot, right? So images, it's very useful there. You can convert it into embeddings and get that. Audio, also same thing. If you want to do a similar audio, whatever audios that we have, you can get that. And then multi-modal embeddings, which models they can convert embeddings, both text and images. So these are some specific ones which do only text, only image, only audio. There are some multi-modal which can handle both images and text, maybe audio and all of that. So this is again, as I was talking about earlier, another representation. Yeah.
If you go back to the previous slides.
Neeraj, yeah.
So let's say that I have some tons of text, right? For example, I'm doing something on Apple products, right? Electronics.
Mm-hmm.
So I did embedding using one of the text embedding. It's all text, right? So I did it by using text embedding. Now, if I'm now doing an embedding of all the iPhones, right? From generation 1 to latest generation, for whatever reason, right? Then that embedding I'm doing with one of the image embedding model here, let's say ResNet, right? Now, all this data, in order to be semantically linked, has to sit together, right? So everything about the Apple electronic as a text and then the image, right? They all have to sit together in a vector database. Is that right? Or will they sit separately?
When you do a semantic search, right, you do only between the text that you do. Now, if any images are related to it, using that results what you get, you can associate an ID to that. And then using that ID, you can retrieve the images that you have stored for that ID. Okay, it's more like you build a relational database again. So when you store your embedding, you store the embedding the text, and an ID to that.
Okay.
And that ID, you can link to the images. You can store all your images and then link to that ID. So when you retrieve from embeddings, whatever IDs that it returns, using those IDs, you can, as a next step, take those IDs and retrieve the images from the database. It doesn't have to be a vector database. If you're not matching on the image itself, you're just matching on the text, all iPhone images that I want. So wherever that iPhone is there in your vector database, it will return you those IDs. So then you can say, okay, I got the IDs. Now I can go to any database now where I have stored my images with these IDs. So that you can get and show. So that is internal. But if you ask the model itself, so it will generate the images. It cannot get you the already existing images. It will generate the images based on your description and what it has been trained on. It knows how an iPhone 14 looks like and so those images it has. So it will generate a similar image and give it to you.
Okay. So are you saying that the two embeddings will be different? Like the text embedding on the Apple will be different from the image embeddings? Because I'm talking
Yes,
about
of course,
an
right?
example, right?
Yeah,
Because that
text
will be
embedding
huge
is different and image embeddings are different.
Okay, so it's a
The
manual process
algorithms
then.
itself are different, how the embeddings. You cannot search image
Yeah.
based on the text embedding.
So then that's a engineering problem, right? It's not
Yes.
something that will, okay.
Yes. So that's how the model, if they know, see, that's how I said, right? If you ask for an image to a LLM model, it will generate based on what images it has been trained on. It will not get you somewhere, unlike Google, where it will point you to some link where you can go and get that image. LLM models may give you the resources, but if you ask it to generate, it will generate on its own based on the training and knowledge it has about those images.
Okay.
Okay. Yeah. Yes. So this is again the same representation of the RAG. So we are, as I said, we take raw data sources. It can be PDF, it can be Word documents, CSVs, or relational data. We split it into chunks. So we'll do that next week. What is chunking? What are various chunking strategies to build the RAG? And then we generate an embedding out of this each chunk. Each chunk, it will have an embedding generated, and we store it in the vector database. This is the first part. And then for the semantic search application, the user asks a question. We use the same embedding model here to generate the embedding and then search the vector database to get the results. And those results, along with the actual original question here, will be sent instruction, context, and query. All three will be sent to the LLM and it will provide the response. So it's basically the same representation. Again, here it's the same. So questions like, what should I do if I miss the last train? All right. And it has information about, what are the various documents, information about which train, where it is, where you are, all based on all of that location. It might suggest you, you can get a hotel room with, with this 200 to 300. It becomes an agentic AI as well, where you want to search for local hotels close by, how much time it will take, and all of that. But each one based on the documentation it has. If you miss the last train, what happens? If there is an FAQ document, if you miss a train, what you can do. So it can get the results from there and then send you all the results from here. This is just one of the scenario that we're talking about. Popular embedding models. Okay, this is what we're talking about. As I said, each LLM vendors who create models, they also have a specific category of models called embedding models, which their sole purpose is to generate the embeddings. Now, as I said here, we have OpenAI. So OpenAI has these two: text embedding ADA 002, text embedding 3 small, there's text embedding 3 large also, which have a dimension and the nodes. So this is the dimension that we are talking about. If we take embedding 3 small, you always get a dimension of 1024. So your output will always be a vector with 1024 elements, a dense vector with 1024 elements in that. If you use 002, it's always 1536 elements in each thing you are. If you use Cohere has 2 models, embedding models, embed English, embed multilingual. So here multilingual, again, it says 50 plus languages you can use to generate the embeddings. It can generate embeddings for in 50 plus languages. This is only if you want to use only English, this is English. But however, the dimensionality is 4096. So it's a high dimensional embedding. So the higher the dimensions, the more complex it is to do the similarity search. It will take more time, more processing to get the similarity search. So if it is your application or your requirement is not very complex, you can go for the smaller embedding models. Like, here we have 384 from Hugging Face, sentence transformer, all mini LM L6V2. Fast, small, great for semantic search. Okay. But if you want to do high accuracy, the same thing from Hugging Face, you have STS Roberta Large with a little more dimensionality, 768 dimensionality here. So we'll see how the dimensionality looks like. And there are more like here. From Google, we have 2. Google Gensym, Word2Vec, Stanford has Glow, Facebook has Laser, NVIDIA has Mnemotex. There are various other models that you have. Where you can go and look at. So if you go to Hugging Face, I'm sure you all must have known about Hugging Face. It's same as GitHub, okay, where all the projects, libraries are there, open source. Hugging Face is also the same, where all the models, machine learning, deep learning, NLP, AI, all models are here. Okay, so if you go click on models, you see there are different types of models here that you can use. Mostly some of them are open source, some of them you have to download off some API and all of that keys. These are machine learning libraries that they use. You can filter with any of them. So I want to do so if it is a text generation, you can do text generation here. If you click text generation models, you get, see, DeepSeek is one of the LLM model that you have. So NVIDIA's this one. So there are so many hundreds, millions of models that you can see here where you can download and use that. And then there is these models, image to text, image text to text, and all of that. We are looking at embedding models, right? Let's see, where is that? Okay, let's see. So embedding, there are 1044 models. Embedding, Gemma, Quen, all of these are your embedding models. If you see multilingual, mini instruct v2.5, okay? You can select any of this, okay? And then see, for example, when embedding, Quen 3, so it will give you example of what this model is and all of that. So you don't have to worry. Just if you are more curious, you can go and read up for, you can open any of this. The main things to look at is this. What is the model type? It's a text embedding model. Supported languages, supports 100 plus languages. Parameters is okay, 0.6 billion. That's how it's built on, how many parameters it will execute or calculate before generating a model. context length is what we're talking about. Context length is one important parameter that I talked about earlier. Can anybody guess what context length is?
Setting the tone, kind of, the prompts, in terms of prompts.
Prompts. Okay.
Yeah. Like the example, like ordering a curry, and then rather than that, explaining in more bit, like curry with spice or vegetarian or
Yeah, that
so.
is that we know that's a prompt. Okay, that's good.
Yeah.
And how we write the prompt. I'm talking about context length here. In this
Oh,
in this context of generating embeddings, what does context length mean?
Output that we get, like number of tokens that we get from uh, any model.
You're close, but it's actually not output, it's the input. So basically it is the how much input it can take, tokens,
Okay.
right? So it can take up to 32,000 tokens at a time to generate the embedding. So 32,000 words, if you put, you get one embedding out of it. So that one embedding will have the meaning of all your 32,000 words. Okay, so that's what it means. Even if you give one word, it will still give you the same fixed length embedding. That's what we're talking about. So context length will be different for each model. So that is the maximum number of tokens you can pass to generate an embedding. This is relevant. Again, will we come back to see when we say chunking, right? Your chunk size will be dictated by this limitation. So if you are using, for example, this model, you cannot have a chunk size more than 32,000 words. So if you're getting a huge, say, a textbook of 1,000 pages, and then you just want to split it by, two parts or two classes, you have to make sure each chunk is not more than 32,000. 32,000 is too high. Normally, it will be much less.
So it's 32 character, right? Not word.
Tokens, not word, not characters, words.
Okay.
Right, I think yes, yeah. So, embedding dimension up to 1024, okay, but supports user-defined output dimensions. So you can choose. It supports multiple. So as I said, some models give you options as to how much you want the output. So this is the output actually. So what is the size of the output that you want for each embedding? You can go from 32 all the way to 1024. It will give you different embedding dimensions that you can use. Okay. So all of these parameters that you see. Now what do sentence transformer usage? It will also give you example how to use that and all of that. And then you can say, hey, how do we make sure which model is good? There is no one straight and good answer for it. There are so many. You just have to go through, choose the popular ones or make sure, you are whatever is based on your use case, you are using the appropriate embedding model. A lot of factors. Say, for example, if you are already using OpenAI, it makes sense to use models from the OpenAI. And again, in OpenAI also has 2 or 3 different models. Then you choose the next level. You kind of go and do analysis. Do I need a model large or a small? Is my use case complex or small? How do I know? You can do again trial and error. Try different embedding models and see how your results are coming out, the semantic search. It may not be just the embedding model. As I said, it can be your number of dimensions. It can be the model you choose. It can be the vector database you choose. It can be the semantic search algorithm that you choose to get the results. It can be the chunk size that you are choosing. It might be the chunking strategy that you are choosing. So all of these parameters will impact your application, semantic search application, or your chatbot. So all of these levers that you have to fine tune to make sure you are getting the most relevant results. Okay, having said that, let's say I have a I want to do a sentence transformer model. See, all mini LM L6V2 that we talked about is a sentence transformers model. It maps sentences and paragraphs to a 384 dimensional dense vector space. Okay, so now the dimension here is 384, and you can use sentences or paragraphs to convert into the embeddings. That's all it is there to it. You can go to, as I said, OpenAI embedding models. If you go, as I said, the new embedding models and API updates. So OpenAI, we all know the models are GPT and all of that. But says it has generated 2 new embedding models, GPT-4 Turbo Preview, GPT 3.5 Turbo model, and all of that. Smaller and highly efficient text embedding 3 small model, text embedding 3 large model. These are already there, and now they have launched these new ones. So this is how embedding models, text as vector, they're representing. So this was like December 22, 3 small, but pretty old. So all of this. Similarly, if you go to any of the vendor, they will have as a category of embedding, they have some embedding models. NVIDIA has one model, like I said, Cohere has, Anthropic has, all of these. Some vendors may not have any of that. And then it also talks about the dimensions. This models, embeddings, all of this. See, max input is this number of tokens that you can give, 8,192. And embedding models. And all of this. Okay, so long story short, that's how the embedding models are given by the each provider and vendor to use. Any questions before we actually get into the action now, the demo part? No? Good. Okay. So before I get into the demo, I want to give a precursor, like how many of you know, I mean, so obviously we'll be doing Python to do all of these demos. As I said, you don't need very complex or very high coding, specialized coding skills, but at least intermediate or medium, any coding language you can use. If you have understanding, you can easily understand the Python as well. And I'll be using the Google Colab and VS Code as initially when we go through this. And I will share these notebooks. All you have to do is go to your Gmail, open apps, and create. If you have a Gmail account, you can go and open the Google Colab and then import this notebook and run that address. So this is for people who have not known what Google Colab is. If you go collab.research.google.com or just search for Google Colab, it will give you an online editor, free to use and very easy, right? There's no client, nothing, configuration, nothing, everything. It comes with preloaded, lot of preloaded libraries and easy to install new libraries, runtime environment, everything. Okay. So just do Google Colab, go to Google Colab here. As soon as you're already logged in, it will give you this. Okay, you can just go say new notebook, and it will give you a new notebook to start writing code and run. So runtime is already here. You don't need to do anything. You can just keep adding the code or text here and keep writing the code. You can execute in smaller blocks, or you can execute the whole notebook as well. Okay. If you just say print hello, just run. That's it. Get the output. Okay. Any files you have, you can upload from your local or wherever here, and then use it in your notebook. You can access the files from here to read it. I'm showing you because tomorrow when we do the application, so I will upload a document to process through all of this, and then we do the semantic search. Another feature here is, you see keys here. This is where you add all your API keys. And then in the application, you can access those keys. I will show you how to add and how to use this, but I'm just showing you a very high level information of what Google Colab Notebook is. And that just put some name and it will be there in your drive anytime you want to go and access your notebooks. Fine. Any questions? You don't need pro plan and all. It will automatically give you the Gemini here, where you can debug the questions you get here. It can automatically read the notebook, suggest questions, suggest answers, rewrite the code for you, and then this Gemini model, you can use it here for your troubleshooting and fixing your code as well. That's the high level introduction. Now, another thing that we want to do is OpenAI API. This is what I will be using throughout this training program in the next few sessions. Of course, you can use any other models. You are free to use any models that are free, but I have been using this for a long time, so it's just comfortable to continue. It doesn't cost much for me, as I've been repeatedly saying. It costs about $10 for the entire training, because it's not very expensive for the kind of demos or exercises, assignments that we do. Okay. OpenAI API key. You go to OpenAI API here, and there should be create an API key. You can sign up and then go ahead and create a key here. Give email address and generate a key. And then I think it will ask for payment details. You can give your payment details. But again, based on the model that you are using, it will charge based on the number of calls you make, API calls to make. And it's not very expensive. I've seen that. Okay, so this is another thing that you may want to set up for yourself before we proceed with more demos, examples starting today. Okay, so set up these two things, and if you have any questions tomorrow, we will take up and that check in the class if you have any issues with that setting up these two things. So having said that, we'll come back. So this is the Embeddings notebook. As I said, I'm going to use the same all-mini LML6 V2 model, sentence transformer model that we are seeing here, this model. And we know that it is a 384 dimensional dimensions vector from Hugging Face. Library is sentence transformers. So to use this model, all you need to do is just import and install the sentence transformers library. How do you install? Let me just say pip install sentence transformers. So pip is a tool that will install all the available Python libraries for you to use. So I will just go and run this. It will install the sentence transformers library. So once you have the library, you import this class from this library, and tell them using this class that I'm going to use this model, all mini LML6v2 from the sentence transformer model. That's it. So your embedding model is ready. And let's say I want to generate embeddings for 2 sentences. My first sentence is hello world, and the second sentence I have is GenAI embeddings are powerful. These are the 2 sentences I want to generate embeddings. All I have to do is take this model, sentence transformer, all mini LML6 model, and then call .encode method function and pass this list of sentences that you want to generate the embeddings. That's all. So this model will take these 2 sentences and generate the embeddings for these 2 sentences, and then it will return a vector of n-dimensional array. N-dimensional array depends basically how many sentences that you are giving it and what is the dimension of each embedding that it has. Okay, now let's say this is done. I will run this now. So the moment I run this, we will have embeddings generated for this.
So internally, does it calling the mini LM API to get those response? Like, or it will work
Yeah,
offline
this
as well?
is this is the model, right? We imported this model in the library. So it will directly call this model to run and generate the embeddings. There is no API here yet. We have not internally, it might use its own APIs, but we have not configured any API yet.
Okay. No, my question is like, does it work offline as well if you use VS Code and we are not connected to internet?
Yes. Internet, no. It has to import from the Hugging Face, right? Any library, once you install, if you have installed it locally, then it will run without internet.
Okay, that was my question. So
Yeah,
once installed,
once
not required
installed, you can use in VS.
Okay.
Okay. Now we have this sentence transformer, all mini LML6v2 model sentences is done. Okay. It has created the embeddings, all of this. With the Hugging Face. Now I want to see what is the vector. Now I will print the first sentence, what I have sent, right? This is the 0 and 1. GenAI embeddings are powerful. I want to see what is the embedding that is generated for this sentence. So I can just go and print this. So this is my sentence here. Vectors of 1. Vectors of 1 will give me the embedding. So this is the embedding. This entire thing is the embedding generated for that one sentence. Okay. Now copy this. Go here. Paste it.
So it generates these many because we have that number of kind of dimension configured, right?
Yeah, I'll come to it 1 second. So how many values are there in this? In one line, 1, 2, 3, 4, right?
Yes.
And how many lines? We have 96. So how many values are there? 96 times 4.
384.
384.
So is this 384 is the dimension size? Can we assume?
Yes.
Okay.
Exactly. That's what we have looked at here, right? Send all mini LML6v2 generates a 384 dimensional dense vector. So your sentence, whatever we have done here, this sentence, GenAI embeddings are powerful, is converted to this is the embedding, corresponding embedding with 384 dimensions. Now this complete vector represents that line. Now let's go and check my first sentence. First sentence is hello world. Okay? Now if I take what is the dimension for hello world, again, it's generated. Just go here. One. Again, 96 into 4. So this is also 384 elements, 384 dimensions. So no matter if your line is small or big or one word or 1,000 words, whatever, up to that limit, it will always give you this fixed length dense vector. This dense vector is what you will store in the vector database. Now, when you store in the vector database, I said, okay, you'll get back the results. And I also said embeddings are one way. It's a one-way lane. You can generate a embedding from the sentence, correct? I can say hello world, I can generate this embedding, but I cannot ask the model, if I give you this embedding, it cannot generate this sentence. Okay, this is only one way. So once you convert this embedding, if I search for something, how do you get the text back? So for that, you also store the actual text also in the vector database. Mostly, you will store 3 things in the vector database once you generate embeddings. First one is a ID. Any generated ID or unique ID or some ID, document ID, whatever, you store that ID. Then the actual text. What is your text or chunk that you are converting into embedding? The third is the actual embedding. So these 3 things are minimum that you store in a vector database. ID, sometimes, it might be optional, but most of the times you also have an ID. So ID, the actual text, and the embedding. Then if you want, you can add a few more attributes also, like document ID or file name, some metadata that you can add to the vector database. But these are the mandatory ones. At least 2 mandatory ones are the embeddings and the text call. Because when you search on the embedding, the text is what actually returned back when you search. Okay. Now, this is how you generate the embedding. So, another example, same thing, sentence transformer. And then I'm generating the embeddings for these 5-6 sentences. 5 sentences. GenAI embeddings are powerful. This is a great day. Greetings to the world. It's bright and sunny. Embeddings are very useful for GenAI and RAG applications. These are more, some sentences are similar to each other, some are not. Okay, some have, a few of them are talking about GenAI, few of them are talking about the weather, and some about just greetings to the world, nothing related to any of this. Now I have all of these sentences now, and then this is the earlier one. Same model.encode sentences, I get the ones, but then I'm using cosine scores. So we'll talk about what is a cosine similarity search tomorrow in the vector database. So for now, just go with me, bear with me with this. All it does is it uses a algorithm, cosine similarity, cosine similarity, to compare the embeddings with each other. So I'm passing the same set of embeddings to compare with each other, n by n matrix, compare each embedding of each line with embeddings of all other sentences, and see how each sentence is similar to other sentences. Okay, using the cosine similarity search. So this is the score. This is the code just to print the first sentence and second sentence, and what is the similarity score between these 2 sentences, any of these 2 sentences. So first I will generate embeddings, and then I will see how these embeddings help you to say which sentences are similar to each other. Good. Shall we go ahead? Okay, let's run this.
Just one question.
Mm.
So these embeddings are generated at 384. So internally, where it stores, like, is there a database or something internally
Yeah,
it is?
that's what I was saying. We'll go to that tomorrow, vector database, where
Okay,
we
okay,
store that. Right now, it's in memory. It's
okay,
all just in this variable here, embeddings, because
okay,
they're just 5 lines. Everything is stored now in this variable now in memory. This we
okay,
will pass it to a vector database to store in the vector database.
okay, fine, yeah.
And
And
that will get you tomorrow. Yeah.
Olive is like it's online, right, on Google platform. If we want to use offline, what application we can download, install?
What do you mean offline?
Like all this coding work we are doing in Colab, right?
Yeah.
If we want to do as installed software, is there anything like that
VS Code
or
you can use.
okay?
Anaconda you can use. Jupyter notebooks you can use. But definitely you will need internet because we will be using a lot of libraries every time to install. So you will be needing the internet connectivity, Wi-Fi connectivity.
Okay. Yeah,
And if
fine.
you are using API to talk to OpenAI API, it does not work in local. Then you have to also download a model like Llama onto your local machine, bring it up on your own server, bring it up that machine, and then connect to your local model, LLM model, and work. So you have to do all of that if you
Okay,
want
yeah.
to do everything local. Okay.
Yeah, yeah. Okay.
Yeah. So because the keys we are generating here, it will go and connect to that OpenAI server, send the request there, and get the response from there. Okay. Now, if you have run this, now see, first sentence, GenAI embeddings are powerful, and this is a great day. These are the two sentences that it has done a search between, it has found the distance between these two in the dimensional space that we talked about, right? 384, all of that. We go here. It's just the one. It's just the one. This. Okay. Now, if those embeddings are plotted in a 384 dimensions, it's just the 3 dimensions we are showing here. In a 384 dimensions, where will those sentences fall and how far they are from each other? That is what we are trying to see here with this program. First sentence and the second sentence, GenAI embeddings are powerful. This is a great day. Is there a relation between these two sentences or these similar sentences, right? So the score it says is 0.09. The score is different from the distance. Okay, you have to understand that. Higher the score means they are closer, similar. If the distance is high, which means they are not similar, so the score will be low. This is the similarity score. Okay, they are mutually what you call inverse relationship. Okay, the more the distance, the less the similarity, right? That we understand. So here we are not talking about the distance. So based on the distance between these two, it has calculated the similarity score. How does it know the distance? It used a cosine similarity algorithm to calculate the distance. What is that algorithm? We'll talk about it tomorrow. Using that algorithm, it has calculated the distance, and based on the distance, it has done a rank score 0.09, which means it's a very low score, which obviously we see these two are not similar. The next comparison is GenAI embeddings are powerful, the same first sentence. Now it is comparing to greetings to the world. This is also bad, 0.08. No similarity. These are two different things. GenAI embeddings are powerful. It's bright and sunny. Again, no similarity, nothing in common. Doesn't make sense. It's two different things. 0.03. GenAI embeddings are powerful. Embeddings are very useful for GenAI and RAG applications. So if you see here, the similarity score jumps to 72%, 0.72. which means there is a high similarity between these two. Now, because this is talking about GenAI embeddings sentence, this sentence is also talking about how embeddings are useful for the GenAI and RAG applications. Okay, now it's found that these two are very similar. They have a similarity score of 72%. Then we say this is a great day and greetings to the world. Again, one is about the day, one is about greetings, not very related, 0.43. Okay. Now, this is a great day. It's bright and sunny. It's again two different things. It's 30%. Okay. This should be actually more. Why it is getting a low score? Because they are both talking about something about a great day. If it's bright and sunny, it should be a great day. Again, these two are two different 0.09. At least this is 30%. This is 9%. Okay. This is again same thing, 32%. This is again 0.04, negative 0.03. Okay. So that's how the similarity scores are between each of these sentences when they do comparison. Okay. Now this is where we get into the next step, where I'm using the OpenAI model, text embedding 3 small, to generate the embeddings. Okay. Same thing. Here we are using sentence transformer model to generate the embeddings. And here I'm using the OpenAI API key to generate the embeddings. This is the model that I have used. This is the boilerplate code. All it does is it takes these 3 sentences and then generate the embeddings using the text embedding 3 small. Okay. And then we have OpenAI API key, which I have used here. I have enabled it so it can use that key to connect to the OpenAI API. And then you can use any model. If you just need to have one key, you can use any model within the OpenAI, like LLM model or embedding model, GPT-4, GPT-5, O3 mini, embedding 3 small, large, all the models from OpenAI you can use with just the same key. However, based on which model you are using, how many tokens it's generating, you will be charged based on that. Okay. But again, as I said, for 1 million tokens, it might be 30 cents or less than $1, 5 cents, 10 cents, something like that for 1 million tokens, which is I think pretty okay, very, very small amount, nothing to worry about. So here I'm taking these sentences and then calling get embeddings method, which I have defined here. It takes this text model I have hard coded here that I use text embedding 3 small. And then get embedding is the method again. Here it is calling same thing. OpenAI dot embedding dot create. Okay, it's creating the embedding for this input, whatever we are sending, using this model and extracting that and sending the what is the actual embedding for this. And we are appending all of this and printing. The only thing you need to look here, no longer supported. Let me run this. I install it. It's giving the older version. This restart session. So now it's using OpenAI 2.11, successfully uninstall old one, collecting new one. So Rajesh, I think you asked, right? So sometimes the libraries change. So you have to install the latest versions. Of course, if you have already downloaded and using the same thing, it will work. But if you want to add new features or new things, you should always use the latest versions. So we
Okay.
done this and successfully installed. And these are the embeddings that are generated using the OpenAI Text-3 small model. If this was the assignment, go ahead and use text embedding ADA002 or any other model and generate the embeddings and see how the embeddings are generated and how the dimensions are matching what it says, the documentation for this model and how they are generating here. You can also get similarity score and see, run with different sentences, your own sentences, and run that. Okay. I think that's a lot for today. End-to-end, what embeddings are, what are the embedding models, how do we generate embeddings, how do we make sure to calculate the distances and similarity between these sentences using the embedding models. Any questions?
Regarding OpenAI, yeah, if you can repeat once again, there is like how it is going to do similarity, cosine search, similarity above. Regarding
I'm
OpenAI.
not doing cosine search here. I'm just
Okay.
generating the embedding and printing it. It will be
Okay.
similar. All you have to do once you get the embeddings, you can write the same boilerplate code what we have done here.
Yeah, cosine.
Yeah, and then use it to do the search. But that's okay. We will be doing a lot of writing to actual vector database and then doing the vector search and all of that. So for now, just understand how the embeddings are generated, what is the dimensions, and what happens if you change the models, what dimensions it will take and all of that. So just focus on that. Okay. Yeah, I will share the recording and the notebooks probably today or tomorrow. Take some time to process the videos and upload. So as soon as you get the access, you can follow the recording and then you can use the notebooks and decks to go through and do the practice.
Yeah.
All right?
One
Yeah.
question regarding dimensions of dimension size. So if size is bigger, that means it will provide like more accurate result.
Yes. Not more. Yeah, you can say that more accurate. It uses more complicated algorithm to search. Basically, it is capturing more dimensions. It's capturing more attributes of your information. Okay, it's say high level search versus detailed search. Okay, let's say you are just classifying people based on height and weight. Okay, now think about if you want to classify more, you want to use the color, you want to use the hair color, you want to use different attributes of a person to cluster more attributes, then your differentiation will be much more. You will get more fine-tuned clusters, right? Okay. Or you are using nationality, or you are using a what you call ethnicity. Use all of those attributes. Obviously, see, if I say Asians, right? Asians can all come in one cluster. But if you want very detailed clustering within the Asians, you can also include nationality. So Indians, Chinese, Pakistan, Sri Lanka, whatever it is, right? So that is the same thing you do when you choose models, how complex or how fine-tuned or how detailed you want to go with getting the cluster.
So these things we don't define it like how you are going to do that clustering or how deep. We just like based on the dimension size.
Yes,
It's
just the
done.
model that is trained that it will generate the dimensions. You cannot suggest use these attributes to do the embedding.
So it's like understood if it is higher dimension, it's doing it already
Yes.
internally.
Yes, right. So we are talking here, when I said it's generating this, right? So these are all the attributes that is using here to generate this. Is it a living being? Is it feline? Is it human? What is the gender, royalty, verb? Is it a verb or is it a plural? So like this, these are all the attributes. These are all the dimensions. Now, if you have only 1, 2, 3, 4, 5, 6, 7 dimensions, only this is what you will get. Now, if you have 500 dimensions, there will be other things about different dimensions that it can use to generate the embeddings. Okay.
Okay.
Okay. All right, guys. Great discussion. Thank you for all joining. All the best. Just go through it. I'll share as soon as possible. Tomorrow we'll continue the discussion. We'll get into the next step. We'll talk about vector databases and how we store these embeddings in the vector database and how we what are the algorithms we use to search the similarity, to do the similarity search tomorrow. Okay.
Thank you, Arun.
Have a good day. Rest of the day. Good night.
Thank you very much.
Thank you.
Thank you.
Yeah, thanks. Thank you.